Assalamualaikum. We are from Group 1 from section 02. We'll explain about our lab heat conduction. These are our group member: Rosino Laili binti Muhammad Yusof, Muhammad Amir Aika bin Azmin, Siti Komaraya binti Ahsan, Siti Rahana binti Abdul Rahim, Nur Iman Balkis binti Syamsul Kamal, and me, Nurul Amira binti Muhammad Nasir. I will explain about introduction to heat conduction. Heat conduction is a heat transfer that occurs when a temperature gradient exists in a medium. The movement of heat from object to another one that has different temperature when they are touching each other are called heat conduction or thermal conduction. A solid medium is used to demonstrate pure conduction. Heat conduction takes places in three dimensions on x-axis, y-axis, and z-axis in real life. The linear heat conduction module simulates one-dimensional steady-state heat transferring the axial direction of an axisymmetric composite solid. And last, radial heat conduction allows the basic laws of heat transfer through a cylindrical solid to be investigated. There are two types of heat conduction. First, we have linear module, and second, we have radial module. For linear module, we will have linear temperature distribution shown in this figure. To calculate the flow of heat through a solid with no constant heat, the temperature and variation of distribution through the solid must be determined first. Linear heat conduction allowing for the investigation for unsteady state conduction. For radial module, we have radial temperature distribution figure like this. Heat flow radially through the thick wall cylinder when the inner and exterior surfaces are both at the same temperature. The radial heat flow through the consecutive layer in the wall must be constant if the flow is steady. The temperature differential must be decreases with radius and the area of subsequent layers increases with radius. Next is the formula of heat flow rate for linear and radial module. For linear, we have Q equal to K times A times dt over dx for linear module. And for radial module, we have formula Q equal to 2 times L times K times bracket T inner minus T outside divided by ln bracket radius outside divided by radius inside. And this is the legends for the formula that I have shown earlier. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amir Bin. Today I would like to present about experiment which is heat conduction. First, the objective of heat conduction experiment is to study the thermal conductivity of heat transfer along a linear model of different element. The manipulated variable amount of heat point used, and then the responding variable is temperature at each measuring point and the distance from heater end. For the fixed variable, 35 mm brass and 35 mm with stainless steel. For the second experiment, the objective is to study the thermal conductivity of heat transfer along a radial model. And then for the manipulated variable, amount of heat power used. And then the responding variable is temperature at each measuring point and the distance from heater end, which is at x. For the fixed variable is 25 mm brass. For the equipment, tools and equipment, first the apparatus and equipment which is unit assembly of heat conduction study bench, main power supply, multi-section bar which is 75 mm brass, 95 mm stainless steel. The 4 is power digital for display heater, and then cooling water, laptop, and lastly another heat sink base. As you can see, the figure 1 is a unit assembly for heat conduction study bench. There are 11 unit assembly that we should know, which is first control panel, heater power indicator, heater power regulator, heater power connector, and temperature indicator, linear model, temperature selector, main power switch, temperature sensors, DAS signal selector, radial model, and linear model. For the experiment setup, as on this slide, we can see that these are the setup of experiment. For the figure 3, this is the setup for linear model. For the figure 3, which is for linear model. For the resilient setup, the software is open and a new task is created. The type of sensor is determined, which is a thermocouple are selected, and temperature under analog input are selected. The channel for each thermocouples are selected as well as shown in figure 5. After determining the channel, run the software and then save it. The select software open the synchronize for the NI and IDAQMS result to the select. In the select and the measurement tab, go to the hardware setup and then synchronize with max configuration shown in figure 8. And then the select is run to record any required result as shown in figure 9. I think that's all for me. Thank you very much.
Assalamualaikum and good day. My name is Siti Kumara binti Hassan, MA18220. I will continue this presentation with experimental procedure and results. So I will conclude this experimental procedure due to insufficient time. Before beginning the experiment, all materials and equipment for each experiment type are well prepared. Next, to start the experiment, the water supply and the heat power regulator are switched on. Then the heat power regulator is adjusted to a desired value such as 10 watt. Lastly, all temperature of the thermocouple is recorded using the loaded software. As shown in the slide, there are two specimens for linear module which are brass and steel element. According to the graph for both elements, the distribution of temperature for different power is giving a negative slope, which indicates an inverse relationship between recorded temperature and the distance from the heater. However, a steel element shows a sudden drop in temperature at a distance of 55 mm for 10 watt due to some gap that cause some heat loss in the contact point while combining the material phase. Next, this is a comparison of temperature distribution within brass and steel element at the same power of 20 watt. Due to a different thermal conductivity between brass and steel, the temperature distribution will be impaired. As a result, the graph shows a consistent rate of heat transfer from section to section for brass element, but for steel element has a variable rate of heat transfer between sections because the thermal conductivity is lower than brass element. Next, the radial module only experimented at brass element only. The result shows an inverse proportional relationship, indication that the temperature gradient decreases as the radius increases. Last but not least, this slide shows the comparison data between linear and radial heat conduction at the same material of brass and the same power of 20 watt. For linear heat conduction, the mass of metal being heated increases linearly with distance, while for radial, it increases in proportion to the distance traveled. It can be concluded that the temperature at each measuring point in the radial module is lower than in the linear module because the heat generated is distributed across a larger radius with a smaller temperature difference. That's all from me. Thank you.
My name is Rosina Laili binti Muhammad Yusuf and my metric number is MA18045. So now I will discuss about our discussion, which is the objective one, that to study the thermal conductivity of heat transfer along a linear module of different elements. So based on our calculation, we can based on our calculation, we can conclude that the brass element has higher thermal conductivity than that of stainless steel. Due to their differing composition of element, which is the brass and stainless steel element have thermal conductivity of 192.1886 and 107.7171 respectively with a power input of 20 watt. As a result, our findings have been proven to be theoretically valid. The reason of uh, this is that the temperature distribution graph for the replaceable steel center component has steeper slope than the temperature distribution graph for the brass element, indicating a higher temperature gradient. The thermal conductivity of substance is inversely proportional to the temperature gradient, according to Fourier's law. In other words, the biggest temperature drop between two connected elements of the same dimension connected to hot and cold reservoir, the lower the thermal conductivity. So, when comparing two materials to be connected with increasing input, larger power generated, more heat that was transferred through homogeneous and composite bars, resulting in higher thermal conductivity.
Assalamualaikum and good day. My name is Siti Rana binti Abdul Rahim, Matric ID MA 18240. I will continue the discussion for objective number 2, which is to examine the temperature profile and also to determine the rate of heat transfer resulting from radial conduction through the wall of a cylinder. So the results of the temperature profile and the rate of heat transfer through the wall of a brass cylinder resulting from the radial conduction through the wall of a cylinder can be affected by several factors. So firstly, the temperature drops as it gets further from the heat source and nearer to the surface of the cylinder because heat energy will flow from higher temperature region to lower temperature region. Therefore, a negative temperature gradient appears because the heat flows in the direction of decreasing temperature as illustrated in this figure. So based on the previous calculation of thermal conductivity for the radial conduction, the calculated thermal conductivity for 20 watt, that is 237.9929 watt per meter degree C, is higher compared to the calculated thermal conductivity for 10 watt, which is 188.9012 watt per meter degree C. So this is actually possible because the temperature difference between T2 and T6 for 20 watt is greater than for 10 watt, as more heat is produced when a greater power is applied. Thus, a higher thermal conductivity will rapidly transfer heat through the specimen. However, for this case, the thickness of the specimen cannot be considered as one of the factors that affects the thermal conductivity and the rate of heat transfer because the thickness remains unchanged throughout the process for both power supplies. That's all from me. Thank you so much for lending me your ears.
Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. My name is Nur Imam Balkis binti Syamsul Kamar and my matrix number is MA19235. I'm one of the member from Group 1. Today I'll be going to present about the conclusion of heat conduction. Without further ado, let me begin with my presentation. The thermal conductivity of heat transfer for different elements, the temperature profile, and the rate of heat transfer resulted from radial conduction were experimentally investigated in this study. From the results of linear heat conduction experiment, the stainless steel element has lower thermal conductivity than brass element. The factors that influence in the process of compare two different materials are involving increasing the power input. The bigger the power generated, the more heat was being transferred via homogeneous and composite bus, and will result in higher thermal conductivity. In the closure, the nearer it to the outer surface of the cylinder, the further it from the heat source will resulting the temperature drop. This was happen as heat energy will moving from high temperature region to the lower. The thickness of the specimen was not changed through all the process for both power supply. It is proof that the thickness is not one of the factors that influence the thermal conductivity and the rate of heat transfer. That is all from my team members for heat conduction experiment. I hope everyone can benefit from it. That's all from me. Thank you.